rectangular. So remember, when you're writing in polar, the first... Oh, I'm still frozen. Oh, you guys have been watching all of this with nothing because it's been frozen. Okay, so polar coordinates are written as r theta, right? R is your distance from the pole. Theta is your direction, basically. So it kind of gives you a distance and a direction. Kind of reminds me a little bit of a vector, right? Okay, so anyway, so if we have a polar coordinate of 30 degrees, that means your radius is 30, your angle is 30 degrees. So how would I convert this to rectangular? Oh my goodness, I'm so sorry. Okay, so x equals r cosine theta, so we would do 30 times the cosine of 30, which is root 3 over 2. So you'd have 15 root 3. And then y is r times the sine of theta, so you'd have 30 times the half, which is 15. So the first one, 15 root 3, 15, which you all... Yes. 100%. Well done. Okay, so the rest of these are all just following the same kind of process. So, good. Beautiful. Yes. Yep. Did you guys have like one person do the odds and one person do the evens? Okay. All right. Yes. Good. All right. Beautiful. All right. So it looks like we could go from polar to rectangular, no problem. This last one would be similar. All right. To go from rectangular to polar, you need to find your r and you need to find your angle. So now we use these formulas. So x squared plus y squared equals r squared. So you do the square root of 9 plus 25, which, oh my goodness. So the square root of 34 would be your r. And then your inverse tan of 5/3. And of course, you have to pay attention to the quadrant. Be careful. So if you are in this case, the second quadrant, your arctan, if it's negative, is always going to give you a fourth quadrant angle. It's going to be a negative. So you're going to have to convert it to a second quadrant angle, right? So this guy, straightforward, root 34, arctan 5/3. This guy, root 52, arctan of negative 3/2. That's really not true because it's that's going to land you in the fourth quadrant. So you really need to do arctan of negative 3/2 plus pi to shoot you into the second quadrant to get that opposite angle, the angle opposite. So, anyway, or you could keep this and do a negative radius, right? Remember that negative radius points you in the opposite direction. Okay. Any questions on going back and forth between polar and rectangular coordinates? Are we all comfortable? Okay, if you don't have these written, the formulas written down, you might want to jot them because you're going to be using these a lot. Okay, but if you already know them, that's fine. All right, so you all did great on warm-up number 1. Let's see how you do on warm-up number 2. Do you guys want to do these on your whiteboards too, or do it? Okay. All right, hang on. Don't get up yet. Does anyone need this slide still? Are you still ready? Yeah, I'll give you a minute. Are some of the lights off? Yes. Why do we only have one light on? Someone must have wanted ambiance. We still have another one off. We only turned on one. Okay. All right. Okay. So, just for fun, no calculator. Let's see how well you remember graphing polar equations. Now, wait, before you all jump up. Okay, this should be pretty straightforward. This should be pretty straightforward. This is a certain shape. This is a certain shape. Kind of. Yeah. But these, when you come to these, just plot, like when in doubt, plot points, right? So if you've forgotten what shape these are, this might be a circle, but we'll wait and see. If you forgot what shape these are, just, pick a few major angles for theta, plug them in and see what you get, okay? All right, try these, just rough sketches on your whiteboards. Let me pause the recording. All right, r equals 7 means you're just using all the different, whatever angle, like angle could be anything, but the radius is 7, which generates a circle of radius 7, right? Theta equals 2 means the radius could be anything, but your angle has to be 2 radians. 2 radians. Remember, if this is 0, this is pi. Pi is around 3, right? This is around 1.5, so 2's over this way. So it looks like all of you got that. The line goes infinitely in both directions. Some of you just have half a line. Be careful. Just because theta is 2 doesn't mean it only goes this way, because you could have both a positive and a negative radius, right? So it has to apply for all possible values of r, which includes positives and negatives. So it's got to go in both directions. All right, number 3 cosine theta. That's a circle. Oh, I'm sorry, I said radius 2. Diameter 3. And cosine, those cosine circles are always shifted sideways, and the sine ones are always shifted up. So anyway, so you get this beautiful circle. There it is. That looks great. Yes, good. Okay, off a little bit. It's not centered at the origin, it's shifted. Okay, good. Those of you who did it. All right. Some of you just did 1 and 2 and then just stopped. You erased them?
We erased our work for 3.
Oh. Okay. All right. 4 minus 3 sine theta. You get a cardioid. Yeah. The circle a little bit in it. Okay. So I see like that group's got it really good. All right. Very nice. Okay. 4 secant theta. Whenever you do, I always like the secant theta graphs. They generate a vertical line. That's going to come in really handy when we get to cylindrical and spherical coordinates, which will be next week. Knowing that when you have a graph of a number times secant, it just generates this vertical line because it's going to allow us to produce something with vertical sides, using angles to create vertical sides. Like if you needed to find the volume of a cylinder in certain types of coordinates, how do you create those vertical sides, right? You use your secant function. And then 5 sine 3 theta is a rose. I always thought these should be called daisies. I think I said that last year because they don't look anything like roses. So anyway, you guys got it. Well done. So good job. All right, so we got to work a little bit on our polar graphs, but that's okay. All right, I have a third warm-up, but let's just do this in our seats. Okay, got a lot of warm-ups today. Okay, so do you remember how to find area bounded by polar graphs? No, that's just a big no. We did this in Calc.
What chapter?
Chapter 10. It was the last unit of the year.
That's why I don't remember.
1/2 r squared d theta.
That's a thing?
It is a thing.
There was a question on the 80s about it too.
Yes, there was. That's good.
At that point, I didn't know how to do that.
Okay, so let me just refresh your memory a little bit. Okay, so for the first one, we have the graph 4 minus 3 sine theta. So 4 minus 3 sine theta is this cardioid right here. Now, in case you've forgotten, one of the things that we liked to do last year, if you have symmetry, was just find half the area and double it. Makes life a little bit easier. But the tricky part is finding where it starts and where it stops, right? Does that ring a bell?
Yeah.
Yeah. Okay. So in this case, since we're not at the pole, the hardest ones are when they start and stop at the pole, because then you have to set your r equal to 0 and solve an equation to find consecutive pole values. But here, these angles, since we're actually off the pole and on an axis, they have to be pi halves or 3 pi halves, or some multiple, right? And you can check. So if I have the side of pi halves, I get 4 minus 3, which is 1, and that matches up with this guy. And if I have the side of 3 pi halves, which is negative 1, I get 4 plus 3, which is 7, which matches up with that guy, right? So we could do, for our area, we would do our angles going from pi halves to 3 pi halves and just double them. You could go negative pi halves to pi halves, right? Anything that produces half of the shape and then just double. Or you could do the whole thing, right? That's okay too. So your formula, you're being taught by Rudolph today. Your formula is 1/2 r squared d theta. So the r squared, that's your r, right? So it's 1/2 times this squared d theta. The only part that's at all tricky is finding the right thetas. So for this one, why on earth did I go 0 to 2 pi? Why wouldn't I go pi halves to 3 pi halves and double? I don't know. But 0 to 2 pi does produce one time around. It takes 2 pi to go all the way around. And I guess 0 to 2 pi are easy numbers, right? So anyway, so 1/2 r squared d theta gives you your area. For the 5 sine 3 theta, so that's this guy. You're going to want to just find one petal and triple it, which I hope I did on the next screen. I don't know. Maybe I went ahead and just did the whole thing. These graphs, though, they don't, it's not like they go petal, petal, petal. They go like swoop, swoop, swoop. It's like a spirograph kind of a thing. Have you ever played with spirograph? Okay. Where you have like little circles with the teeth, right? So it spins around and produces the shape. That's what this kind of does. It goes zoo, zoo, zoo like that. So anyway, but what you need to do is just find 2 consecutive spots where it hits the pole. So we'd have to set 5 sine 3 theta equal to 0. So that's just gone. So you get 3 theta equals 0 or pi or 2 pi or all the multiples of pi. So then you divide by 3 and you get 0 pi thirds, 2 pi thirds, dot, dot, dot. So then all you need are 2 consecutive. Doesn't matter which 2 you pick, they just got to be consecutive. So I'm going to go 0 to pi thirds and triple it. So, okay. So for this guy, hey, look, that's what I did. So I did 0 to pi thirds, I tripled it of 1/2 r squared d theta. Okay. All right, so today we are doing double integrals with polar coordinates. We're going to find area, we're going to find volume, we're going to do all kinds of fun stuff, all with polar. Tomorrow is center of mass and centroid. I don't know if I can screencast that in advance. I think it's, I don't know. Maybe I should make tomorrow quiz day, but then I gotta still screencast Fridays in advance. Either way, I have to screencast it in advance. I don't know. I gotta figure something out. Maybe I just come to school tomorrow and make this room all bad. So, all right. All right. So 15.3, double integrals with polar equations. So, reviewing what we learned last year. You don't have to write this down. Area of a circle is pi r squared. Okay, everyone's comfortable with that. So, do you guys remember, let's see if you remember this. When you are approximating area under a curve, you approximate it with rectangles, right? You break the curve into rectangle chunks. You add all the rectangles together. To find exact area, you take the limit as the number of rectangles approaches infinity, right? Okay. When we are approximating area bounded by some polar region, what you have to do is break it into sectors, right? Like pie pieces. So you have to find, so it helps if you know the area of a sector, and then you take the limit as that change in your angle approaches zero, right? Because it's the angle that determines the width, that delta theta. You want that delta theta to go to zero so that your sector becomes just a line, right? And then you add all those radii together and you get the area. All right. So, area of a sector is the proportion of the circle used by the sector times pi r squared. And when you clean it all up, you get area of a sector equals 1/2 delta theta times r squared, which is how we built up the integral formula that we just used, which is 1/2 r squared d theta, right? So that's your basic integral formula to find area of a polar region, is 1/2 r squared d theta. Now we're going to take it up a little notch. Okay, except I can't raise this up. I don't want to show you what's under here. Here, wait, I can do this. There we go. Wait, make this wide. Wide. Go down. Extend. Pull back down. Ha. Okay. All right. Suppose we have some radius r, and we're going to find an area of this funky shaded region. And so we have our r sub 1 and our r sub 2. So we have these two different radii, and we're just going to call r the average of those two. So we have, I don't know if you can see it, but this from here to here, that's r sub 1. And then from here all the way to here, that's r sub 2. So r is some average radius in between. Can we use that concept to find a formula for the area of the shaded region in terms of r, delta r, and delta theta? All right, so, and again, you don't have to write this down. This is just how we derive the formula. All right, so area of the whole sector. So area of the whole sector is 1/2 r squared delta theta, right? Okay, so everyone gets that. Area of the part that's not shaded, this white space right here, would be 1/2 delta theta times r sub 1 squared, right? So r sub 2 is the whole thing. R sub 1 is this space. If we subtract them, we're going to get what's left, right? So we subtract the 2, and we get what's left. So we have 1/2 delta theta times r sub 2 squared minus r sub 1 squared. But there's something cute about r sub 2 squared minus r sub 1 squared. It's the difference of squares, right? So if we factor it, we get 1/2 delta theta times r2 plus 1, r1, times r2 minus r1. Well, r2 plus r1 over 2 is the same as r, right? And then r2 minus r1, well, r2 minus r1, that's the difference between the two radii, right? So that would be delta r. So from this, we end up getting area of this region being delta r times r, or delta theta times r times delta r, or r delta theta. Now, how does this translate into double integrals? Because what we're going to find when we set up our when we set up our double integrals, which I think I have written again on the other side, but that's all right. So is whatever your function is, so you have some function in terms of r and theta, or x and y that you'd have to convert to r's and thetas, right? So you have some function in terms of r and theta. Whatever that function is, that's like kind of like your z value, right? Because remember, r and theta, again, those are just coordinates in a plane. So all you're doing is using a different type of coordinate system to generate the coordinates that you're plugging into your z function. So we have our z function, but what do we have to do this times? And then you would go up. So you'd have your, like, I don't know, A to B. I'd have to write. I got to show you, like, on another slide what this means. You have some function, some r equals something to r equals something, right? And then theta equals something to theta equals something, right? Whatever those are. So these are like the boundaries. It's just like what we did with x and y. These are the boundaries of the region in the r theta plane, just like in the xy plane. This is still the height of your z function, but it's going to be written in terms of r and theta. Here's the new thing. So when you're in polar, whatever you have for your function, your z function, has to get multiplied by r, and then dr d theta. So my brain, whenever I think polar, my brain thinks RDR, RDR, RDR d theta, but I always think RDR. Oh, RDR. I don't know why it reminds me of party har. If anyone even knows that expression. Okay, it's old time laughter. Anyway, so that's how I remember it. All right, so let's get into some formula, some formal formulas. Okay. All right. So here's the thing. There's two different ways these problems could be presented. So you could either have some region that's bounded between two values of theta, and it's this like r stuff that's changing. You have r equals some boundary and then r equals some other boundary. If that's the case, then you want your theta to be on the outside because those would be constants. You'd have theta equals a, theta equals b, and your r's would be your functions. So you would have theta going from a to b. This is how I wrote it. So some function in terms of theta, an inner boundary, and some function in terms of theta, an outer boundary, times your function, r dr d theta, which of course you would have to convert. Instead of xy, you'd want it in terms of r's and thetas. And x is r cosine theta, y is r sine theta. So that's just converting. Okay. If your region is bounded between two r values, where your r goes from a constant to another constant, then you'd want your r to be on the outside, because that has your constants for your boundaries. So you would have an a to b, this is alpha and beta, but anyway, you'd have an r going from a to b, and your theta functions would be, their theta boundaries would be functions. And again, you'd have still r, but instead of r dr d theta, it'd be r d theta dr. This doesn't come up very often. This is the one you'll see way more. Yes, Jack? Those are constants. So it depends on which alpha beta you're talking about. The top one, yeah, those would be thetas. The bottom one, those would be r's. And are you okay? He looks like befuddled. Yeah.
The one in the middle says H2 of R.
And this is H2 of theta.
Yeah,
that's wrong. It should be H. They should both be H2 of R. Sorry. Did I freak you guys out? Yeah. Oh, thank you. Yes, Jack? It just depends on what your region looks like. most of the time, we'll do the first one. Because most of the time, your region will be bounded by some polar function that will be r equals something, and then you'll just find a beginning and ending value of theta. Kind of like what we're doing in that warm-up, the one that you guys didn't really do, I just walked you through, right? So whatever your region is, some function where it's like r equals something in terms of theta that bounds your polar region, which is the vast majority of the way that we write polar regions, and then you have a starting value of theta and an ending value of theta. That's when you use the top one. The only time you use the bottom one is if you have a polar function solved for theta and your r's are constant, which could happen. It just doesn't happen very often. I don't know if I've ever seen a problem written like the second case. Good. Any other questions? Do you guys all have this down? Okay. Okay, so first we're just going to practice with just a generic integral. So here we go. Evaluate the integral of f of xy equals x squared plus y bounded between the two circles. Now I'm already like eating my words because this would be second case. So between the two circles, x squared plus y squared equals 1 and x squared plus y squared equals 5. So this would be one of those cases where you have a d theta dr. Why? Because your r's are constants, right? So, okay. So when you do these, if you want to set them all up in terms of x's and y's and then convert, you can. That's up to you. I usually, I don't know what I do. But anyway. So this is the same as r squared equals 1, so r equals 1. You don't have, like, you know how with x's, if I have like x squared equals 1, x is plus or minus 1? With r, the minus is irrelevant. It's the same as a positive, you just have more angles, right? So so we don't have to worry about the plus or minus as long as we use angles to take it into account so that we get the 1 all the way around. And then the same thing here, so your r is root 5. Again, just using the angles to go all the way around. So to do our base region, if we have this circle and this circle, so this is our base region. It's like a big donut. I know that this is r equals 1 and this is r equals root 5. So what angle would I have to use to generate the whole thing? 0 to 2 pi. Just go all the way around, right? Okay. So, all right. So what I've done here is I've got my 0 to 2 pi for my angle. I've got my 1 to root 5 for my r. Oh, I did do. They're all constants. Oh, you can go either way because it's all constants. It really doesn't matter. Yeah. So I did do r d theta. I do like RDR better, just because I like saying RDR. So, anyway. Okay. So, but we can't integrate yet, because what's wrong with this?
It's not polar.
Right, we have x's and y's, so we got to convert the x's and y's. What does x equal?
R cosine.
Okay, our cosine theta. What does y equal?
R
Our sine theta. So you're going to have to convert this to an r squared cosine squared theta and an r sine theta. Before you integrate, watch out, because you still have another r there. So before you integrate, you got to multiply the extra r in. So once you get it all set up, you should have r cubed cosine squared plus r squared sine. Go ahead and do your antiderivative with respect to r and plug in your r bounds. And then if you want to kind of hold off there, we'll do a spot check because something tells me you're going to need a little help with the antiderivative of cosine squared. So combining like terms, once you do your antiderivative with respect to r and plug in your numbers and combine like terms, you end up with this. How do we antidifferentiate cosine squared? We use our power reduction identity for cosine. Cosine squared is equal to 1/2 times 1 plus cosine 2 theta. You got to know it. So sometime, if you don't know it, you might want to write it down. But cosine, here, I'll write it over here. Cosine squared is equal to 1/2 times 1 plus cosine 2 theta. And sine squared is equal to 1/2 times 1 minus cosine 2 theta. So whenever you hit a cosine squared or a sine squared, you got to do a power reduction. Yes?
So could you set the cosine squared equal to 1 minus sine squared?
It doesn't help you though. You still got to reduce.
I think is it possible though?
Well, sure, but you're not making your situation any easier.
It wouldn't help at all.
No. Okay, so now the antiderivative of 3 with respect to theta is 3 theta. The antiderivative of cosine 2 theta, well, it's 3 cosine 2 thetas, and 3 just is a multiplier. But let's just look at the cosine 2 theta. The antiderivative of cosine 2 theta is sine 2 theta divided by 2, right? You always got to divide by the slope of the argument, as long as the argument's linear. Okay, and then the antiderivative side is negative cosine. Does that not ring a bell? I just heard a what? Once you get there, you plug in your 2 theta and you plug in your 0. The nice thing is that the sign is just gone. Or 2 pi, sorry, not 2 theta, 2 pi.
Integral like the sine component with the coefficient on the 5 and 5. Wouldn't the minus 1 turn to plus 1 for this? Would it say?
I did minus out front of the whole thing.
So it's not just okay.
Yeah. When you do minus in front of a fraction that's out front like that, it's applied to the entire fraction. The fraction is considered a grouping symbol.
Okay.
Yes, Laura.
I'm kind of confused on why we use theta on the outer integral instead of r.
So I personally like to do RD theta because it's more common and it's my comfort zone. You could have done this RD theta to r, which actually, it wouldn't have been any easier. As a matter of fact, no, it would have been about the same level of difficulty because you're still going to have to integrate squared trig terms anyway. But the reason that we switched it was for no reason other than the fact that since all 4 of your limits were constants, you could go in either order you want. So, yeah. Doing good. How are we doing? Yes. Where are you wanting to cancel them out?
Before plugging them in. So like after integrating.
After integrating. Oh, okay. I think so, but I'm nervous saying yes. Yeah, I think so. Okay. I'm gonna say that, but I'm nervous about it. All right. Okay. So we're gonna just find the area inside of this little 4-leaf clover here. So we want to find the area inside r equals 3 cosine 2 theta. There's no z in this one. The z is just going to be a 1. So because we're not finding volume, we're just finding area. So when you're finding area, it's the exact same thing as finding volume where your z function just equals 1, right? So see if you can figure out, this one, symmetry will be in your favor. I would do symmetry for this, absolutely, right? So you're going to have to find the r values, like a starting and ending r value, what you might want to multiply it by, and then think about what your limits are going to be. It has to be a double integral. No singles, that's cheating. So double integral. So r goes from something to something, theta goes from something to something. Of just 1 times r dr d theta. Find where it intersects the pole. You set your r equal to 0, so just divide by 3, that's good. So then you say, all right, 2 theta equals, what angles have a cosine of 0? Pi halves, 3 pi halves, 5 pi halves, negative pi halves, and so forth, right? Okay. So then divide by 2, so you get pi fourths, 3 pi fourths, 5 pi fourths, dot, dot, dot. So we would pick any 2 consecutive. The first one is the first time you're at the pole, and the next one is the next time you hit it, and that would generate 1 leaf. So once you've got your thetas, your r is just going from 0. So it's like an inner boundary to an outer boundary. So if my r's, think of the r's as being like this. I don't know if you guys remember this from last year. I kept kind of drawing like this when we were doing our polar area. Our r's are all going from 0 to this function, right? So our lower limit for our r would just be 0. Our upper limit would be the 3 cosine 2 theta.
That's the whole thing. The whole function. Alright. 0 to 3 cosine 2 theta.
Oh, yeah.
Yeah.
How do you know if the R's first equal or the
If the function, I'll give you, like, if your boundary is solved for r, it's going to be an r dr d theta. 99% of the time, it's going to be an r dr d theta. The r boundaries, 0 to 3? Because 0 to 3 would be a constant r equals 0 to a constant r equals 3. We don't want r to be a constant of 3. We want r to go out to this function, right? Remember, these are the the values you're plugging in. So as theta goes from pi fourths to 3 pi fourths, so that generates like these different values of theta. But we got to do it times all the different radii. So we get all those different ones. If r was just a constant of 0 to a constant of 3, you're just spitting out 3 for every r. But it's not just 3. All right. Once you have the setup, did you guys evaluate the integral already?
No.
No? Okay. Well, in this case, we're not finding volume, we're finding area. So area means that our function, our z value, is just a constant of 1. Because area is the same as volume with a height of 1, right? So if you just have a z value that's always 1, you're going to generate area of the bounded region instead of, I mean, you also get volume with height of 1.
You know what?
You understand the difference? Like, okay, shh, quiet please, guys. So if we had a function here, if we had sub f of x, y, okay, please stop talking for 1 minute. These guys right here, this shape, this is the base on the r theta plane, and then z comes out of it, right? So if we have a function here, if we have some z function, what you're getting then is a volume of some surface within that cloverleaf boundary on the r theta plane, right? If I don't ask you for volume, if I just ask you for area, then there's no like area formula. There is only volume. But if your height is always a constant of 1, it's the same as the area, right? So really, when we're using double integrals to find area, you're doing the volume formula, but just using a function value of 1. But it's always in polar times r d r d theta. So antiderivative of r, 1/2 r squared. Plug in your limits. 9/2 cosine squared 2 theta d theta. Aren't you glad you know the power reduction formula for cosine?
Yes.
Right? Okay. So this becomes what? 18 times 1/2 times 1 plus cosine 4 theta. Okay. And then that's just a number. So you anti-differentiate. Be careful because the antiderivative of 1 is theta. The antiderivative of cosine 4 theta is sine 4 theta divided by 4. Is that okay? Did you guys get it?
This is the first time this unit I got something right the first time.
Oh. Talk to me about questions. So Josh, how you doing?
Good.
Are you doing good, or you just saying that?
I'm just really mad at it. Cross out a Y because I wrote it wrong. So now my notes look really bad.
Don't see my notes? I haven't notes anymore. Just you do all the scratch work.
All right, I'm gonna skip this. And we're gonna go to this one. Oh, sure. Oh, did you have a question or you just
like having this just bothers me. It just bothers me so much.
okay. Good. Anyone else need more time or have any questions? Ryan, how you doing in the back? Yeah? Okay. All right. So we're going to jump to this one because I know we're not going to have time to do all these examples. All right. Use polar coordinates to find the volume of the solid region bounded by the hemisphere. So we do have symmetry if you want to use symmetry. The hemisphere, z equals the square root of 16 minus x squared minus y squared. And below, by the circular region, x squared plus y squared is less or equal to 4. Really, I think it could just say equals. I don't know why they say less or equals.
Yeah, I was confused by that.
So boundary is a boundary. But anyway. Okay, do you guys want to try to set it up yourselves? Start like from scratch and I won't even help you? No. See how you do? No?
Yeah, sure.
Well, if it was like forward, like just regular behavior, it can feel like from 0 to 2, from like 0 to 2 to 4, that's not a but you can't do it for it's 4. So I guess it's harder.
Regions that are bounded by circles are really easy in polar.
Yeah, I thought they were rectangular.
No, much easier in polar than rectangular. Way easier.
In rectangular, wouldn't it be like 0 to 2? Or...
Yeah, but then you got your functions. You'd have to do the square root of 4 minus x squared, positive and negative. That's an ugly, right? Where here, you just have your r going 0 to 2. Much easier in polar. Right? And your theta to just go around the circle is just 0 to 2 pi.
Well, I guess r equals 4.
Close, r equals 2. Because r squared equals 4, right? Guys, don't forget x squared plus y squared equals r squared. Right? X squared plus y squared equals r squared. And look for tricks like, right?
That's way easier.
So your base region in the r theta plane is just this circle with a radius of 2, right? How do I generate that circle? Well, my r goes from what to what?
2.
0 to 2. R goes from 0 to 2. Theta goes from what to what? 0 to 2 pi. Hi.
Hi. I should give this to Lily.
Oh, okay. She's right there. So your r's and your thetas are all constants of your boundary, which means you could do dr d theta or d theta dr. I personally tend to prefer dr d theta, but that's just me.
Is this like
This is actually a very easy, regular, old U substitution.
Oh, yeah, it is, because like he uses.
Okay, so if you do a U substitution, so your U, let's see if we remember U sub, 60 minus R squared, du is negative 2R dr, negative 1/2 du equals R dr. So you end up with So this stays 0 to 2 pi. I'm not even going to write my limits because I've got to convert back. So we have negative 1/2 u to the 1/2 du, and then your d theta just kind of comes along. So this becomes u to the 3/2 divided by 3/2 or times 2/3. So then you get negative 3. How did I get negative 1/3? 2. Let's see, 3/2, 2, oh, times 2/3. Yeah, negative 1/3. Okay, so negative 1/3 u to the 3/2, right? So that's your antiderivative, which I just convert, like put my u back in with r's. You could keep it with u's, but then you got to convert your limits, right? Either way. Okay. So, all right, so once you do that, you plug in the 2 and you plug in the 0, and you end up with negative 1/3 times 24 root 3 minus 64, which then gives you, oh, I didn't even distribute, I just left it. Okay, this whole thing is just one great big constant, right? So then the antiderivative of this is this whole great big thing times theta. So you end up with this whole thing times theta from 0 to 2 pi. So it just ends up being this whole big thing times 2 pi. How did we do? We tried.
Yeah.
We're going to have a lot of practicing to do.
So we won't get a calculator to do anything.
There is no calculator on this whole test.
Times negative 8. It's negative.
But you know what I do give you? Because students asked for it last year, and I don't care about the cost of copies. We've been talking about copies a lot in the school lately. I give you a whole page for every problem. So some problems you only need like a quarter page. I give a whole page for every problem. So anyway,
For me, it's every page.
you get lots of space.
Every page.
Okay. All right. Okay. So.
Oh, God.
All right, this is kind of a fun one. So, proof. You got this. You got this. It's not really a proof. Really, all you're doing is just deriving the formula for the volume of a sphere, right? Okay. Okay, I might skip this one. Okay, oh, I had one more example. I gotta find it. I might skip this, because we actually just did this exact problem. The only difference is that we did it with a radius of 2 instead of a radius of a. By the way, so this was a hemisphere. So if this is a hemisphere, bounded by this region, so if you think about it, if you square both sides, you get x squared plus y squared plus z squared equals 16. It's a hemisphere of radius 4, except it's only in this circular region. That's kind of funky. So what shape are you actually getting? You're getting a sphere with a dome on, you're getting a cylinder with a dome on top. You're getting a part of a hemisphere, but you're cutting it off like through a circle through the middle. So it's, you get, because the radius of the circle is 2, the radius of the sphere is 4. So if you were to picture a whole sphere, right, with a radius of 4, but then, you bound it by this circle of only radius 2, so pretend it's like an this thing, right? What you end up with is the stuff inside the cylinder plus the little bit of sphere that's like domed on top inside the cylinder, right? Kind of fun. So anyway, so it's not the same problem as the next one, because the next one's actually easier because it's just a constant radius hitting the r theta plate. All right, but I was looking through my, I don't know if I still have it up. I have one more example that I want to pull out. Oh, gosh. Here, let me see if I can find it. Chapter 15. Just, we used to do polar over 2 days. Here we go. So we're kind of squishing. Okay. Go. Here we go. Oh, okay. This is fun. All right. So let me copy this page. Copy. Paste. There we go. Save. Find the volume of the solid that remains. So it's kind of, now this is exactly like this one. So now we have a sphere of radius 8. We're drilling a hole of radius 3 through the center, and you're finding the volume of the styrofoam that remains, right? Kind of fun. It's actually easier than you'd think. A little hint, both your r's and your thetas will be constants. See if you can just do the setup. Come on, you can do this. Let me stop the recording for a bit. I'm looking on the r theta plane, right? Well, the sphere would hit the r theta plane in this big circle of radius 8, right? We're cutting out a hole with a radius of 3. So this region, that's the region that we're integrating over. So your double integral, the limits of your double integral would just be the r's and thetas that generate this. Easy constants. You could do this real easy. I'll help you with the function in a minute.
Would it be like from 3 to 8 and then like 0 to 5?
Yes! See?
We're not given like the. If we want to do like the function, then what's the f of r?
I'm sorry, I'm listening to Rishi. Arshi, what are your r's? That is correct. What are your thetas? Okay. If my lower boundary is r equals 3 and my outer boundary is r equals 8, then my r's go from 3 to 8, right? So r equals 3 to r equals 8, and I want to get that all the way around, right? What makes me go all the way around? 0 to 2 pi. Okay, no, stop saying, we've talked about this, right?
It's so long to understand such a simple concept.
It's not simple, right? If we say this out loud, it would be like saying, Sujesh, I can't believe you didn't get your radius and theta angle measurements correct for your double integral in polar coordinates for calculating the formula for the area of a hemisphere with a hole drilled through the middle. I mean, this is hard stuff, right? Okay, so anyway, all right, z. How do we find our z, right? You gotta have a z. Well, we know that the sphere, equation of a sphere centered at the origin, right, is x squared plus y squared plus z squared equals r squared, right? Radius of 8, so 64. So your z, would be plus or minus, z equals plus or minus the square root of 64 minus x squared plus y squared, or r squared. Now, in order to eliminate the plus or minus, this is truly symmetric, so you could just do the positive times 2.
Okay.
Would you have to multiply that by 2?
You would. Okay. All right. Good work today. I know it was a hard day. No, stay in. Stay in. Bell hasn't rung.